we are very happy to have Sepehr from Caltech, and he will tell us about the quantum gravity in the lab.
Thank you so much for introduction, and thank you for the invitation. So I'm Sepehr Nezami, a postdoc at Caltech, and I'm going to talk about quantum gravity in the lab, which is, and this talk is mostly based on two papers. I think the screen is a bit, is there any way to fix it? It's just like, is it visible from the back? No, I'm just saying it's stretched, it's small.
I had to go into display settings.
Oh, I see.
If you do want it to be the right size.
I mean, if it's visible from the back,
I think it is visible.
Okay. So
if you can't see it, there's lots of room up front.
Okay, and yeah, so it is based on these two papers with my collaborators Adam Braun, Ron Karibian, Stefan Leichenauer, Henry Lean, Grant Salton, Lenny Susskind, Brian Swingle, and Marco Walter. And because I was worried that maybe some parts of this thing have some of you have heard this talk or a subset of this thing, I added a bunch of new results or just like new comments and some of the ongoing work. And let me start. So our goal here is to explore the connections between quantum information theory and quantum gravity, and more importantly, during the NISQ era. And it's partly motivated by a SYK model, which suggests that many could be the generic quantum systems could have a gravitational dual. So we are looking to suggest experiments that could be potentially run in near term. And so in particular, we want to simulate the non-gravitational side of the system, the holographic duality in the lab, and detect the signatures of existence of a holographic dual in the bulk. So from the potential signatures of a holographic dual, we choose a very simple one, and that's basically the fact that things fall in gravity. So what we want to simulate the boundary of a system and see if things fall in the bulk, the gravitational bulk, as we expected from the gravity. So the basic setup is this traversable wormhole setup, when you have two boundaries and you release a signal from one boundary. You act by some coupling that I'll explain later, and then you expect to receive the signal from the other side of the system. These two thick yellow lines are the parts that you run in the experiment. So you have 2 points in your lab, simulating a system like a SYK system, and you expect to receive the signal. So from the point of view of the signal, the operator or object that you injected in the boundary, the operator is really free falling from one boundary to another boundary, and that's why we basically saying this is a test of existence of holographic dual. So if you don't have a holographic dual, you don't expect to receive the signal from the other boundary. And this type of geometry is, of course, called the traversable wormhole geometry. And so in this talk, I'm going to discuss the traversable wormhole geometry and dual quantum circuit. And I'm going to particularly talk about the state transfer versus the operator transfer protocols. And I'm going to say that the same quantum circuit really sends information basically in two different regimes. The first regime is a low capacity, high temperature, and late time regime. This is kind of unexpected from the gravitational picture. So you really write down the circuit that is motivated, which is exactly the same as the gravitational picture, but you see that it not only teleports in the holographic regime, it also teleports in this regime, which we call mostly holographic inspired teleportation. And the second regime is really when the particle falls through a wormhole. And a part of this talk is really explain these two regimes and talk about how you can really distinguish them. And then for the second regime, I'm going to talk about size winding and gravitational dual operator size distribution. And I'm going to talk a little bit about the effect of noise and different approaches for measuring the traversable wormhole signal.
Sorry, is in a first regime just quantum transportation?
I mean, everything. I mean, because you have.
But it's especially like exponential.
Yeah, I mean, even the holographic regime can be interpreted. I mean, there are all different types of quantum teleportation because, I mean, eventually you have an entangled system and you send a signal. It should be teleportation in disguise, but there are different types of teleportation.
To follow up on that, if you go back one slide.
Oh, yeah.
I'm sort
signal in this language, when you're just thinking about the boundary theory, is a sign of teleportation. It could be one that is more complicated or less complicated, but it's not a sign of gravity per se.
Right.
Conversely, you could have a situation where you have a gravitational dual, but you're not setting it up in such a way that you have a traversable wormhole,
Right.
and then you would have no signal. So I don't understand the logic behind the connection that you're establishing there between this receiving of a signal and there seems to be no arrow of implication in either direction.
So yes, you're right. So this is basically what I was talking about here. So I'm saying in the second regime of teleportation, I'm going to tell you that when you receive the signal, it comes from a traversable wormhole, but that essentially requires some level of interpretation and knowing more about the system. So I'm also explaining that in the actual gravitational system, what is the holographic dual of a traversable wormhole on the boundary? So that's the kind of a theory work. And I'm telling you that if you receive the signal and if your boundary behaves in a certain way that is a signature of gravitational teleportation, then you're in the business. But also, I'm just saying that you can, in the first regime, receive the signal, but you can interpret it as simple a scrambling experiment. So
why are we so interested in this teleportation / wormhole way? I mean, the question of whether a theory has a gravity dual could be tested in many other ways, including ways where we don't set up two boundaries but just one, and we ask about certain behaviors of I don't know, some low point functions, some scattering, and so on. We could always ask whether that has a gravity dual or not.
right.
What is it about teleportation / wormholes that makes this question sharper, or maybe it's more applicable in actual?
So the first thing is,
Yeah.
So I think the first point, I mean, there are several answers for this question. One is that the fact that this circuit, this dual to this traversable wormhole picture teleports from a quantum information point of view is very surprising. So you scramble your system, you lightly touch everything. I'm going to go through that. But then you scramble it further, and somehow your signal appears from the other side. So it is quite an unexpected phenomena, which makes an interesting experiment. At the same time, it is, given the thing that you can do in the NISQ era, I think among the things that you can do in the NISQ era, like random circuit simulations, if you could do this, it really sits at the top of in my opinion, is one of the most interesting things that you can observe. So the question is, if your question is what you can really learn about gravity from this, which is, I think, if I understand correctly, is what you were asking.
One thing I'm confused is in the NISQ era, we don't really have good methods for error corrections. So even when you observe something, how do you know it's an effect from the thing that you wanted, not an artifact from your noise?
Yeah, that's a very good question. So this is like any other. So the reason it's not really just like a near term, like 3-year NISQ thing. I mean, the first regime, which is inspired by holography, is being done right now. Vincent will talk about this, I think. But the second regime, which is really the gravitational one, requires more control. But the good thing is that unlike quantum field theory, that you probably need many, many qubits. Here in the SYK model, you might see good signals like in order of 100 degrees of freedom. So it is closer and it is interesting. And the fact that you don't really need to, the fact that at least in this kind of models is a very generic phenomena. You don't need to fine-tune things is also inspiring. But of course, something that I'm extremely interested to learn and just like know more is that what exactly are the things that you can learn by simulating the system. You can actually read out small n corrections probably. These are hard to compute from string theory stuff. But the very interesting question is that can you actually test systems? Are there systems that you can actually simulate and you don't know if they have a holographic dual, but they could be, but you cannot really, currently you cannot really compute things about. So that's my other question.
Sorry, how do you decide whether or not it has a
So this is kind of what I'm going to explain. So in the talk, I'm just going to tell you that this circuit really teleports in two regimes. One of them is just like a scrambling. And one of them, if you see the signatures, the phenomena of this signatures of the second one, it looks like gravity. For example, the scrambling one just teleports with any sign of coupling, but this one really teleports with one sign of coupling. And yeah.
But this doesn't necessarily have to do with the gravitational theory being UV complete or being a string theory in the bulk.
And
Signature of time.
yeah, I mean, eventually you have to just like read off signatures and signatures to convince yourself, I think, if you have access to the boundary. I think it is a signature that has a simple circuit dual, at least conceptually from information theory point of view. I don't know about the hardness of the real experiment, but conceptually it is something that you can propose.
In response to your question, isn't part of the thing that's nice about these gravity-inspired protocols that they are able to distinguish scrambling from decoherence, for example?
Yeah. So this is a work by, I guess, Norm and Benny and friends. Yeah. So that's great. Yeah. So yes. So this is a actual holographic picture. You have two boundaries, and you inject your signal by some quantum channel, and you release it in the bulk, and then you have some coupling, and then you receive signal. The circuit dual of this thing is that you start with a thermal field double state, which is the state at time equal to 0. You time evolve backward. You inject your signal in. So here you have n qubits on each side, or n microns on each side. But when you inject the signal, you touch very few of them. By this quantum channel, you inject your signal. You time evolve it further. And the left-right coupling for the case of qubits is very simple coupling. So you have z left, z right, zi left, zi right qubits. So you just like couple them in pairs and sum over this coupling, and then you normalize everything by n. So the strength of this coupling on each qubit is very small, and then you multiply the whole thing by a g, by coupling a g, which is order 1, and you time evolve further, and you expect to get signal out. And this is what I was saying, that this is really surprising from quantum information point of view, that you injected your signal here, you scrambled at this point, you lightly touch each qubit, and you time evolve it further, and you get this signal back from the other side. So we want to study this circuit and see how it works. So I'm going to study two different regimes. The first regime only requires a scrambling dynamics. And here I'm going to implement my channel by injecting a qubit. So basically I trace out the qubit that was here, and I put a fresh new qubit on a known state. And I expect to get it out from the other boundary. So this type of teleportation works at long times when TL and TR are both long, and works at very large temperatures. So this is all the conditions are not expected to, the actual teleportation through the wormhole is not expected to work. You need low temperature for actual wormhole. And you can even see for a non-holographic system, like a chaotic Hamiltonian, just like a GUE, like a GUE ensemble, when you put random numbers in every matrix element, you see a good signal coming out after a certain time, after a scrambling time. But the downside of this regime of teleportation is that it can actually teleport only one qubit. It cannot even teleport one qubit. So it is highly limited in capacity. Yeah.
When you say you get the qubit out, do you have to do any decoding operation?
You have to act by a Y operator, a single Pauli Y.
Okay.
But that's it.
It comes out on a specific qubit?
On the same qubit that you put in.
I see.
Yeah. So the pairs are entangled here one by one, and there is a notion of order of qubits because you have a TFT and just bell pairs. So it just like knows where it should come out. But this is very low capacity. So basically, as I said, if your time evolution is a random unitary, if you replace every one of this time evolution with random unitary, you still get your state back. So this is a 2 design, like all the scrambling things. But if you have things like spin chains locally look like blocks of random unitaries next to each other. So there are cases that you can cheat and send more signal as long as they are separated spatially. But if time gets longer and longer as you go down, then the whole spin chain again looks like a random block of unitary that can teleport only 1 qubit. So random unitary is capable of sending 1 qubit. So I'm going to very briefly explain that how this thing works. I don't really need you to follow the details, but just like get a sense of the fact that it is easy. So at infinite temperature, you can really put this. I'm define U to be this time evolution operator. At infinite temperature, I can just do the simple transpose trick and put this operator to the other side and do a simple circuit modification, and I get this kind of signal, circuit, which is equivalent to this circuit. And you can see that by 2 design calculation, the net effect of all these time evolutions and this left-right coupling is only giving a phase to 1. So here we have 1 qubit, you have another qubit. And is a phase to giving, the net effect of everything is giving a phase to the maximally entangled state, the standard maximally entangled state here. So it basically gives the phase e to the ig to the Bell state and does nothing to the other state. So really what happens is that it gives a phase to a single, the whole procedure gives a phase to a single state in the entangled Hilbert space. And the task of changing a phase of a single state is not really a powerful enough operation to send many qubits, but it's powerful enough to send 1 qubit. And that's why this type of regime of teleportation is capable of teleporting only with scrambling.
So what are you mentioning about interaction, switching on and off?
Yeah, so this time, the coupling is just like instantaneous coupling. It's not like Moldosena Xi, which is on all the time. So it's just like you touch it and turn it off. Yeah. So I'm not going to talk about it that much because Winston is going to talk about it, but I'm just saying that this model is simple enough to run numerical experiments on, and you can see that, for example, for a Rydberg Hamiltonian kick-rising model, you can have numerical results that are showing signals even with 7 qubits. And the numerical results are perfectly matching the analytical formula. So it is basically solved. And so this is another work with John and his ongoing process when surface student Andrew Yates, when we studied the effect of noise in this kind of systems. So here we're talking about the single qubit decoherence noise. And you can do this analytically, or you can do simulations. And you can see that here there are green areas. The green areas where when you have an error, nothing bad happens. You still get the signal. So you can obviously see that outside the light cone of your output qubit, everything is green. So if an error happens there, it's fine. Here, you have a little bit of green as well, because you know that this left-right coupling lightly touches every qubit. So the information here is kind of, when you're going through this unitary, is kind of encoded in a quantum error correction code. So individual corruptions will not destroy your signal. So somehow you have some nice error resilience to errors near the coupling. And you have some extra type of an error resilience here from the simulation that we don't know why. But so this is kind of a good news that at least in some parts of the circuit, you don't really care about errors because information is already encoded. So if there is no, how am I doing with time? 25 minutes, okay. So, so now if there is no question, yeah.
Can I ask one quick question?
Yeah.
What happens in this first regime when you take the temperature beta and change it for the thermal field double?
Yeah, it just the signal. I mean, I don't know in generic case, but one case that you can analytically compute everything is the case when your Hamiltonian is just a totally random Hamiltonian, GUE ensemble, and in that case the signal goes down.
So it just goes down.
Yeah, it just gets worse. So now I'm going to talk about the second regime. And here, I think it's generically advised to give motivation and talk about the details. I'm doing kind of the opposite here. So for a few slides, I'm going to talk about the size distribution, operator size distribution, operator growth. Please bear with me. And after that, I will connect it to the traversable wormhole story. So as it was explained very nicely by Tommy today, so I'm going to talk about the operator size. And everything I'm saying here can be interpreted for both Majoranas and for Paulis. But I'm sticking with Paulis because it's easier to just explain. So what you have is you start with a local operator like local Pauli like x, y, z, and you time evolve it. And as Tommy said, you expand it in the Pauli basis, a multi-qubit Pauli basis. And you get some coefficients. And this, as you increase time, these coefficients, the support of these coefficients goes to larger and larger operators because your operator size grows. So this is like kind of a picture of individual CP coefficients. So this is a real axis. This is the imaginary axis. And when at early times, the size distribution of operator is really concentrated near small operators. But as time passes, it just grows and gets wider and wider. And so this is not a real data. But this is what you expect for normal operator growth in K-local systems. But now I'm going to look at the thermal operators, so which means that I have to thermally dress my operator. The way I choose to do it, and I will explain why like this, is by looking at rho beta to the power of 1/2, which is my thermal density matrix, and multiplying it by O of t. So I just multiply the thermal density matrix to my operator. And you can see this is proportional to e to the minus beta over 2 minus ith, or e to the minus iht. And now, product of two Hermitian operators is famously non-Hermitian, unless they commute. So this quantity is non-Hermitian, which means that these coefficients, the CP coefficients, are not necessarily real. They could be complex numbers. And something that you can compute and see, for example, based on the calculation of Xiaolang and Alex Stryker, you can just analytically continue their calculations and see the following phenomena, that in the SYK model, in the large Q SYK model, size distribution, as you increase beta, kind of winds. So it obtains a phase linear in size. So this is, again, imaginary part. This is the real part. And as I'm increasing temperature, instead of this coefficient, instead of being just like totally randomly instead of being just randomly distributed on the complex plane, for each size, you get somehow the coherent distribution of operator, the coefficients to be on a line. And this is what we call size winding. And as I will say that this phenomena, in a couple of slides, I will say that this phenomena is, we believe that this is the dual to the traversable wormhole picture, and this is what makes traversable wormholes work. And but before going there, let me quickly explain to you why from just like multiplying this operator, you expect to get a phase like this. And so let me talk about the microscopic mechanism. I can't do it with Pauli's, but I'm going to do it maybe for only the SYK model. So here is your SYK Hamiltonian. You have these couplings, and you have 4 Majoranas. And you have this time evolution of a local operator. And I'm just going to split this time evolution to n steps and write it 1 minus n. So this is just like an ordinary expansion of an exponential. So I have a simulation time now that goes from 1 to n. And I just implement these operators one by one on both sides to really create the operators on the left-hand side. So now suppose that the operator O is a Majorana fermion of a certain size. It's indexed by this V. After one computational time step, you multiply it on the left by 1 minus 1 over n beta over 2 minus it, and multiply it on the right by 1 minus 1 over n ith. So there should be an h here, sorry. So the way that this operator grows is that you see that it still has a factor of psi v, so the original fermion, but you have extra terms. And these are the terms that show how your operator really grows and how when you multiply terms of your fermionic for your SYK Hamiltonian to your simple operator, how you get new and newer terms. So let me explain how this formula works. So when you multiply a Hamiltonian term, a 4-Majorana term by your fermion, sometimes, basically in most of the cases, if the size of the operator is small, you just don't collide, and you have an operator with the size increased by 4. So most of the time, you increase your operator size by 4 because you're multiplying a beta term. In some other cases, in lower percentage of the cases, which is proportional to 4 times size of the operator divided by n, you increase the size of your operator by 2. It's just like the ordinary way that you look at operator and just like time evolve it and get larger and larger operators. In lower percentage of cases, you just don't time evolve, and sometimes in very, very rare cases, your operator gets smaller as you look at this commutator as you evolve your time. Yes?
It looks like a lot of these terms disappear when you send beta to 0, but some of them are still there. Do you expect this behavior, this size winding, to also happen at infinite temperature?
No. No.
So what happens to the terms that linger when you send beta to 0?
So beta, so this is real. This is real. These are all real operators. When you send beta to 0, you just evolve by commutation instead of multiplication. So you generically don't increase your operator size by 4 at each step when you multiply on both sides. You only increase your operator size by 2. So you will. So this guy exists. So you could increase or decrease your operator size. But some of the terms don't exist. So, and you don't get size winding because your operator is real. The O of t operator is.
The Majoranas are complex.
Sorry?
The Majoranas are complex. So the I times the Majorana is real.
Yes, yes. So basic idea is that you know how if you have product of q number of Majoranas, if q is equal to 0 or 1 mod 4, you don't need to put an I to make it Hermitian. If it's 2 or 3 mod 4, you need to put an I. So that reason, when I increase the size by 2, I put an I to make sure that this operator is still Hermitian. So this is a pattern of operator growth for something like SYK. Now I'm interested in operators of relatively small size. So I keep repeating this procedure. I start for a small operator. I multiply by these two left and right matrices, and I get a slightly larger operator, and I keep doing this over and over again as my operator starts growing. So you can see that when the size of the operator psi v is still relatively small, when your size haven't evolved, only the first 2 terms are really the ones that contribute in your operator size growth. The first one makes the coefficient the same. I mean, if the coefficient is real, it just multiplies the coefficient of this psi v by a real number. The second one multiplies the coefficient by a complex phase, by the number 2t plus I beta over 4. So it has a phase of approximately beta over 2t. So if you look at the operator fermions of size L, if this is the distribution, after one layer application of this operation, you get operator of size L plus 4 by the first term, which are just like a scaled version of this phase, these coefficients. But you also get the operator of size L plus 2 with the coefficient that is the complex number. So you slightly rotate linearly by a complex number. So as you keep applying this kind of operation, as you make your time evolution operator, size distribution could either stay real or get a linear phase. And the fact is that when your operator size is relatively small, the time evolution, this evolution is really dominated by this term because it's proportional. The probability is 1 minus 4 times size of the operator divided by n. So if this number is small, this probability is close to 1. So you're mostly evolving real. But when you're near scrambling time, the operator size gets large. This guy will dominate. which means that your operator size originally starts growing until it's getting near the scrambling time. Operator size is large, and then you get factor from the second term, and you get a linear. What happened? Oh. And why am I muted now? I think my Zoom actually died. Sorry.
Can you unmute your Zoom?
I don't have a Zoom anymore, I think. Somehow it's launched.
No,
Don't need
I
that?
think it
It's
was
on
on
the
the
left,
other
right?
window. If you just go to the left a little further. Yeah, right here.
Oh, my screen share somehow.
And unmute yourself.
Yeah. Sorry, I don't know what happened. So basically, this procedure, just the time evolution, just gives you a linear phase when you look at this operator rho beta to the power of 1/2 times O of t in the size distribution. Of course, this is a very toy model, so I'm not considering different coefficients. So system could potentially go to spin glasses and stuff. So this thing may not be. This is a very toy version of what's going to happen. But in a YK system, this happens precisely as I explained. Yeah.
I just wanted, the fact that this non-Hermitian part, the beta evolution, happens like in between dynamical evolutions. You're doing a little bit of dynamical evolution and then a little bit of e to the minus beta h.
Right.
And then a little bit, so they're occurring. And this is physically different from another thing I could do, which is to prepare a state in the thermal ensemble and then subject it.
I'm actually not doing that. If you look at here, I'm just actually evolving by a little bit of beta over 2 minus IT, and then by a little bit of IT.
Okay.
So I'm not really alternating between these two. I just like devolve.
Sorry,
Yeah.
I think my question was done. So, all right.
No.
Yeah.
Yeah. So is it kind of clear that what I'm doing here? Is there any question? Yeah, in any case, you expect to see this phenomenon of size winding. And now I'm going to connect it to a gravitational picture. So look at this picture when you insert an operator on the lower left of your Penrose diagram. So this is explained by, you can write it as O of L times minus, O of O left of time minus T times thermal field double. And if you write thermal field double as rho beta to the power of 1/2 times maximally entangled state, it would be this operator. And you expect this operator to jump to the other side after the action of your left-right coupling. And this operator, when you do transpose trick, is exactly the same thing, but with a different order. So it is explained by rho beta to the power 1/2 time of left times O L of minus t. It's just transpose trick. So somehow the role of left-right coupling should be to swap these two operators. And I'm going to explain how it's working. So as I said before, this is your initial state operator in the lower left, and the corresponding operator is OT times rho beta to the power of 1/2. Sorry, I changed the sign of t, but it's fine. And the operator appearing on the upper right is the same operator as I explained, but with a different order. So these are Hermitian conjugates of each other. This operator has a clockwise winding. This operator is the exact same thing with the counterclockwise winding because it's a complex conjugate. You complex conjugate all the coefficients. The left-right coupling, basically the size operator. So it gives a linear phase to operators of different size. So what it does is basically it unwinds this distribution, unwinds in the opposite direction. So this is the role of the size operator. In this way, it maps this distribution to the other one. So this operator is going to map to the other operator, and this is how traversable wormhole works. So it maps the operator on the lower left to operator on the upper right. Is there any question at this point? Yeah.
Yeah, why do I need to do the time evolution after the fact? This makes it look like all I need is the coupling to turn the left picture to the right picture.
Yeah, so the time evolution is really here, right? I mean, when you write this operator, you
Okay.
yeah, you have the time evolution already implicitly. Yeah. So now I will basically more or less end with the momentum size correspondence. So it was it's expected that people just like Lenny, I didn't write the full citation, sorry. So Lenny and Adam and Henry Lin, Maldacena, and Ying Zhao basically were working on this idea that the momentum of a particle that's falling in the bulk is really dual to the size distribution or the derivative of the size distribution on the boundary. But now we have not only the size distribution, we have a phase. So it really kind of suggests that this winding size distribution is really the momentum wave function of the particle falling in the bulk. And from that, you can read the location in the bulk because the phase of the momentum wave function is really the location of the particle. You can read off the location of the particle, and you can see the NSYKD exactly matches the particle that's getting exponentially closer to horizon. So it behaves as you expect, and it adds the phase to the picture of size momentum distribution. And the role of this left-right coupling is really shifting the position of this size distribution. And the fun fact is that you can see just like this kind of signatures of this size winding in non-gravitational systems, like in random Hamiltonians, but it's very, very weak, and the operator coefficients are not on a line, so they are like on an ellipsoid. So this is kind of, I kind of expect this nice size winding to be a signature of gravity because, as I explained, it's dual to traversable wormholes. 5 minutes. Okay, thank you. I'm going to end. So, but this is also an ongoing research. So we are, instead of running a traversable wormhole, we are actually looking at ways to measure the size winding phenomena, and hopefully that would be a stronger signature for gravity. We are looking at different ideas like using shadow tomography or different techniques to really read off the size distribution and the size in the size and the phase in the size distribution. And we're looking at how much the quantum memory could help in this process. So, and the one nice thing about the operator, one nice thing about this size winding picture is that you only need one copy of the system because it's really defined on this operator and not on the two-sided system. That could give you a benefit in near-term experiments, a factor of 2 in the number of qubits. So with this, I would end with some open questions. So we're looking at to see if there is any connection with the size winding and maximal chaos. And this is other question that I asked. Is there any other model that you think could be implemented in near term or in relatively near term and could teach us something about gravity? And with that, I think I would end.
Questions?
Did you discuss the capacity of the second, like how many qubits you can send in the second?
No, I haven't done that. No, but Maldacena and Stanford Yang have studied that, I think. So the basic idea is that you can connect. This is, for me, this coupling was acting basically on all qubits, but you can act on a small number of qubits. And I think they properly study this, depending on how many qubits that you connect, how much information you can send. And it is more than one, for sure. It just you can get a large number of qubits around. Yeah?
Do you expect to be able to do something similar with two operators coming in?
Yeah, that's a very good question. I don't know. I think that's, yeah, that would be a nice picture because instead of one particle, you could have two particles. I think that's.
Do they interact behind that?
I don't know. Yeah. So the problem is that, I mean, I made some arguments about the operator size here, but this is all very rough. And models that I know the operator size having computed is large QS by K, and basically random unitaries. Random Hamiltonians. Totally random Hamiltonians as GUE. So those are a bit boring from the point of view of gravity. And I don't know any other model that you can explicitly calculate. Maybe there are models that you can reason in this way. That would be nice. But yeah, so it's kind of fun that this phase is really encoding the location of your particle as it's falling in the bulk. Yeah.
So you said that generic systems also have this kind of first phase teleportation thing, where you can only do 1 qubit in a giant unitary. But then they can also do this size winding thing.
Yes. So I think if you have something like SYK, it will teleport like a normal holographic system. But then after the scrambling time, the first regime actually kicks in. So it would teleport with the particle actually going through a wormhole. But I mean, there is one minor point I didn't talk about. That is this: you can really observe teleportation or just information transfer by looking at the 2-point functions. So the actual gravitational picture is really nicely explained when you compute the 2-point functions of left and right. But the teleportation, the late time teleportation, was best understood in the actually resetting the qubit and sending a new qubit over. So it is just like a state injection. So you don't look at the 2-point function; you measure fidelities, like what you do. So, but except that. That thing works after scrambling time, a little bit at this scrambling time. And this holographic one works before that. So if you look at the random Hamiltonians, you see the signal actually starts 0. It gets a peak, which is for a little bit of size winding, residual size winding that you have in this kind of random Hamiltonians. And it just saturates to a plateau.
What I'm trying to drive towards is, like, if I had a generic scrambling system, to go back to the original questions, how would I know if I saw some teleportation? What signatures would I look for that would tell me that this is size winding versus just?
Yeah, I mean, you can do. I think you can do different things. So basically, what happens is that when you look at this 2-point functions with the coupling injection inserted, really, you're looking at the Fourier transform of the size distribution at the value g. So you can really play with g and reconstruct the size distribution. Of course, I mean, we could have, yeah.
You do that, and if it doesn't work, if you're varying g all around, and
yeah.
It doesn't.
Yeah, and this
change the success rate of teleportation, and you know it's not.
Right. So something that happens is that in the first regime, you can teleport with positive g, and you can also teleport with negative g's. But in a holographic regime, you can actually teleport only with one value of g and nothing else.
Okay, and this is what you were saying earlier.
Yeah.
Okay.
So and at the same time, the time that it works is a signature of gravity. Should work a little bit before the scrambling time. I think you expect it to require a larger g if you are getting closer to a scrambling time. Sorry, a smaller g when you're getting closer to a scrambling time. It has to work in low temperature. So there are a lot of things that consistent with one picture and not consistent with other picture.